Alright, so in this video we're going to continue our discussion on volumes. In the previous videos we looked at three examples and this example will be a little bit different. So I'd like you to find the volume of the solid obtained by revolving the region bounded by y equals the square root of x. So the first thing I want to do is sketch the curve y equals the square root of x, and I hope we all know by now that y equals the square root of x looks something, let me go ahead and do it this way. Let me see, let me make it a little bit bigger. Maybe it looks something like that. So that's our function y equals the square root of x. And then it says and the curve y equals x. So now we have two curves here. So y equals x, maybe it'll look something like this. Let's see. So there we go, y equals x, and I want to rotate this region. So the region that they're referring to, it looks like they're referring to this region right here. So we want to rotate this region, or they want us to rotate this region around the x-axis. Well, how in the world is that going to look? Well, if I think about, first of all, just reflections, and I think about reflecting this y equals x across the x-axis, it looks something like this. So maybe it looks something like that. So that would be y equals x reflected across the x-axis. And now if I try and reflect y equals the square root of x, well, that might look something like this. I'm really testing my drawing skills here. So it'll look something like that. And then again we have this as a region. But I want you to keep in mind that this is not a two-dimensional figure that we're looking at. What we've actually created, and it looks like we're just focusing on these regions here. So what I'm going to do here is I'm going to go ahead and just erase. I'm going to go ahead and erase this right here, so we're not going to need that. It looks like I'm only looking at this area here. And I want you to think a little bit what you've just created by rotating around the x-axis. You've essentially created some type of solid, or some type of figure that looks kind of like this. So again, you know, think about like maybe like a little you know, round cup, and then you stick like a little cone in there, but it's hollowed out here. It's hollowed out right here. So there's nothing going on in this middle space. Well, how do you find the volume of this? Well, it looks like the only region that we have that's solid is this up here. But what I want you to think about is the same idea or I want you to apply the same idea we applied when we were talking about finding or using the disk method. And the same idea is going to apply here. So imagine if you were to take a slice. So if we take a slice here. So if I take a slice here, just like that, then I'm going to have this type of slice, I'm going to have this type of shape come out. So I'm going to draw that over here. It's going to look kind of like this. Now, in previous videos, what we would do is just find the volume of this cylinder. So we would find the volume of this cylinder, and then we would kind of just accumulate infinitely many cylinders, and then that would give us the volume of our figure here. The problem is that with this figure here is that it's hollow. We have an empty space here. There's nothing here in this center area. There's nothing going on. So what we actually have is some type of donut. If you want to think about it like a donut, we have like a donut with a hole in the middle. This is called a washer. You'll read this in math books. You'll see the washer method, and you'll see the disk method. This right here is called a washer. So what I want to try and find again is the volume of this solid region. Now I want you to pause the video and think about how you could find the volume of this solid region without this hole. So assuming you've paused the video and given it some thought, maybe you had some type of intuition that says, look, why don't we just ignore that the hole is there altogether? Let's just pretend that this is all solid, and I can find the volume of a whole of the entire cylinder, and then what I can do is subtract. I can maybe take away the volume of this little hole, and that'll leave me with the volume of whatever's left. And if that was your intuition, then you're absolutely correct. That's exactly what we're going to do. We're going to go ahead and find the volume of the outmost cylinder. We're going to find the volume of the entire cylinder, and then we're just going to subtract the volume of this purple cylinder here that's on the inside, and that'll leave us with everything in green that you see here. So let's go ahead and do that. Let's go ahead and try setting this up. So again, the volume, I'm just going to go ahead and refresh our memories. The volume of a cylinder is equal to pi r squared times the height. Well, it looks like we're going to have to work with two cylinders here. We have the outer, and then we have this inner one that we need to subtract. So the volume here, the volume of this slice right here is going to be pi, and I'm going to start labeling these things. I'm going to call it r squared, but I'm going to call it r out for the outer radius. And what I mean by that is I'm talking from the center. I'm talking about from the center all the way to the outmost region, which is this guy right here. So this is my outer. This would be my outer region right here. So it would be pi r squared out, and then again I have the h. But remember, the h is going to get replaced with this dx because that's our height here of this cylinder. And then we're going to subtract. We will take away the volume of the inner cylinder. So what does that look like? Well, that's going to be pi r squared in, because now we're working with the inner radius, and we have dx. And again, if you look at the picture here, we're talking about this radius right here. So we're looking at that circle there on the inside. So hopefully this is the intuition you had, that you're going to find the volume of the outer cylinder and then take away the volume of the inner cylinder, and this is the formula we get. What we now need to figure out, or what we need to plug in, is first of all is we need to write our radius in terms of x. Well, if we go back to our original drawing here, and you think about the radius here for a second. So let's talk about the outer radius. So if I talk about the outer radius, I am talking about from the center, or from where we're rotating, we're rotating around the x-axis. So I'm talking about from the x-axis all the way to the upper part of this cylinder here. So it looks like I'm right there, and it looks like that is some function. Y equals the square root of x. So it's going to be some square root of x, depending on whatever that x value is. So for example, if this x is 4, then this height right here, this radius, would be the square root of 4, which would be 2. But think about it. I could have cut it. I could have made my slice, I should say. I could have made my slice way over here, and then I would have some type of different height here, some type of different radius. But it would still be the square root of x. It would just be a different x over here, right? It would just be a different x. What I'm trying to get at is that the outer radius is just your outside function here. It's the square root of x. So if I come back to my formula and I plug in pi, and instead of r squared, the radius is my function, the square root of x squared dx. And then we're going to have minus, and I'm going to have pi. Now I have to think about the inner radius. Well, if I look at the inner radius here, it's the distance from here to here. But again, it's given by the function x. So again, my radius is just x squared dx. Now I'm going to pause the video here. I'm going to stop the video here, and in the next part we'll finish off this problem because I'm running out of time here.